Hi, so welcome back to the channel. This is Analysis of Statically Determinate Frameworks 1, Internal Forces, 2.1, Introduction. In Chapter 1, we have shown that the response of structures to actions is measured by the internal forces and by the deflections. For certain relatively simple structures, it is possible to find the internal forces simply by considering static equilibrium, these structures being called statically determinate. In this chapter, we shall describe methods of finding the internal forces of statically determinate frameworks. As a starting point, we shall consider in the next section what is meant by static equilibrium. We shall review the basic concepts of this branch of classical mechanics in sufficient detail to give a complete basis for the structural analysis presented in the remainder of the book. However, the subject will be presented as concisely as possible. Classical mechanics is extensively described in a great number of texts, and a very thorough and clear treatment is given by Merriam. So, static equilibrium. In order to understand the meaning of equilibrium, we recall the definition of forces introduced in Chapter 1, Section 1.4. We first consider forces acting on particles, which are defined as hypothetical bodies having finite masses but being infinitesimally small in size. If then a single force P1 acts on a particle of mass m, as in figure 2.1a, the particle is given an acceleration of p divided by m in the direction of the force. If several forces P1, P2 and P3 say act together on the particle, as in figure 2.1b, the particle accelerates as though it were acted on by the resultant P4 of these forces, P4 being the vector sum of P1, P2 and P3. P4 can be found graphically by summing P1 and P2 using the parallelogram law or vector addition, and then summing the resulting vector with P3 as shown in the figure. The concept of equilibrium is derived from the case when the resultant is zero, for then the particle does not accelerate. If it thus remains either at rest or moving in a straight line at any velocity it might have had before the application of the force. In most structural problems, we are only concerned with stationary states. The particle is then said to be in a state of static equilibrium under forces P1, P2 and P3. Static equilibrium can be expressed as a simple relationship between the components of P1, P2 and P3. Let us consider first for clarity the two-dimensional case in which the forces lie in the xy plane of the global coordinate system. The parallelogram law of vector addition is equivalent to saying that the scalar components of resultant P in the x and y directions are equal to the sums of the scalar components of the three forces P1, P2 and P3 in those directions. Thus, P4x equals P1x plus P2x plus P3x equals the sum of Pix, where I equals 1 to 3, equation 2.1a. P4y equals P1y plus P2y plus P3y equals sum of Piy, I1, 2, 3, 2.1b. Static equilibrium of particle then requires that the resultant P4 is 0 and is expressed by the condition that the sum of Pix, I1, 2, 3 equals 0 and Piy, I1, 2, 3 equals 0. Equations 2.2 are called the equations of linear static equilibrium. The extension of 3 dimensions and any number of forces n simply involves adding an extra equation in the z components and assuming from 1 to n. The corresponding linear static equations can then be concisely expressed as sum of I equals 1 to n, Pi equals 0, where Pi is the column matrix of the scalar components Pix, Piy and Piz of the force Pi. Oops, sorry. Example 2.1. Suppose a particle is acted on by two forces, P1 and P2 of magnitude 10 and 15 respectively, and directed as shown in figure 2.2. We wish to determine the components of a third force P3 which will maintain the particle in static equilibrium. Figure 2.2, so we've got P1 equals 10, P2 is 15. Okay, so 15. P2 is 15 in the X with the YZ plane at 45 degrees. The scalar components of P1 and P2 are calculated as follows. P1x equals 10 times cos 60. Remember, oh yeah, cosine of, oh yeah, it's got two angles there, hasn't it? So it's measured in two angles. 60 and 75 from Y. Ten cos 60 degrees equals 5. So cos 60 must equals 0.5. P1x, P1y was 10 cos 75, it was 2.59. P2x equals 0. P2y equals 15. Oh yeah, because 15. P2 is in the YZ plane only, so P2 has no x component. P2x equals 0. P2y obviously equals 15 sine 45 because the vertical component is for sine, that's opposite over hypotenuse, 10.61, and P2z equals 15 cos 45 equals 10.61 kilonewtons. Also, we also have, since the square root of P1x, so P1x squared plus P1y squared plus P1z squared, all square rooted, equals P1, equals 10. Then P1z equals 8.26 kilonewtons. Thus, letting the unknown components of P3 be P3x, P3y, and P3z be obtained from the equation, from the equilibrium equation 2.3. 5 plus 0 is P3x, 2.59 plus 10.61 plus P3y equals 0, 8.29 plus 10.61, P3z equals 0. Therefore, P3 equals minus 5, P3's x equals, oh yeah, oops, sorry, P3x equals minus 5, P3y equals minus 13.2, and P3z equals 18.87. That's the, I'll go through these all again, but that's the first part of chapter 2. Please can you like the video? Please can you subscribe to the channel so that I can keep on doing more videos on this subject. I've got some very interesting problems coming up on this. There's some really good ones, not just this, but some good ones, yeah, that we were looking at this formula for statical determinacy later on in the chapter. So please can you keep on liking and get some more subscribers, and I can keep on making videos. And I'll come back to this. The next part of this chapter is forces acting on a body of finite size, but I'll do that in the next video because we've got 10 minutes. Thanks for watching. Please tune in for the next video. Thanks.